Okay, hi everyone. So today I'm going to talk to you about my PhD work, which I just finished at UC Berkeley with Dr. Kevin Healy. I'm going to tell you about improving drugs that are used for treating patients with diabetic retinopathy. So diabetes is it's a disease that affects hundreds of millions of people worldwide. It accounts for about 8% of the US population and about more than 300 million people around the world. Diabetic retinopathy is one of the worst symptoms of diabetes, and you can see that one of the main symptoms is this abnormal blood vessel growth in the retina of the eye. So what ends up happening is that these new blood vessels that form actually have very loose junctions, and that means that blood can actually escape from the blood vessels and go on the retina, which causes these blind spots that you can see here. So it's very debilitating if this disease affects your central vision. And about 80% of patients with diabetes will develop symptoms of diabetic retinopathy. So the main protein that actually induces the growth of these blood vessels is called vascular endothelial growth factor, called VEGF is how I'm going to refer to it in this talk. So what happens is that this protein, VEGF, is able to bind to the surface of these blood vessels on the retina and induce the growth of new blood vessels. And again, these new blood vessels are very leaky, and so they leak out their plasma, they leak out their blood cells, causing these blind spots. And so this is what the new blood vessels would look like on the retina, something like that. And these are the pools of blood. So the way that this is traditionally approached is by injecting drugs such as Avastin, Lucentis, Macugen. Some of you may have heard of Avastin and Lucentis. These are actually also used in treating cancer because it's the same pathological thing that happens, this excess blood vessel growth. And so what happens is that patients get injections with Avastin and Lucentis directly into their eye, and that causes regression of these blood vessels. So they go away, and it helps for a certain amount of time. But so here I'm going to give an example. At the time of injection, this is a drug called Lucentis. We're injecting it into the eye, and sure, there's a good amount of drug there. But after a couple weeks, not much of that drug remains, and that means that there's a short active time of this drug in the eye. Patients are required to get monthly injections directly into their eye. This causes pain and discomfort, and basically the disease gets worse if patients aren't coming back at the right time. And so this is the main problem that I was trying to address. I was trying to increase the amount of time that these drugs that are currently used stay around in the eye. And so the way I did that was I used this sugar molecule. It's this large sugar molecule called hyaluronic acid, and I use a protein that targets that. I use a drug that targets that exact protein, VEGF. And so I make these large drug polymer conjugates. And so they're bigger. And so you can imagine that something bigger is going to travel much slower through a jello-like matrix, which is what's in the eye. So what you see is that at time of injection into the eye, there's a lot of drug. And after several weeks, a lot of that drug still remains, meaning that it would be more active over a longer period of time, and patients would require less injections. So some of the main takeaways from the first half of my work was that when I do this attachment of the drug to the polymer, I don't see any decrease in activity. And also I showed that based on the size, that these new drugs that I made actually do end up moving a lot slower through jello-like matrices. And actually this attachment of the drug to this sugar molecule protects it from enzymatic degradation, meaning that when you put it into the eye, it's not going to get degraded as quickly. And so these initial results led me to believe that this is going to work in animals and possibly in humans. So the next step was to look at animal studies. So the major takeaways from the work that I did in animals was that when I injected this drug, this new drug, into the eye of rats, it actually stayed in the eye 10 times longer if you look at the half-life. And so what ended up happening then was that I took it into a mouse model. This mouse model is basically the same thing that happens in the human eye during diabetic retinopathy. So when I treated the mice with this drug, it was actually much more effective than the drugs that are currently used. And so this means that this approach has strong potential to improve drugs not only for treating patients with diabetic retinopathy, but other ocular diseases as well that are affected by retinal angiogenesis, including macular degeneration, but also other diseases in the body as well. So we can reduce the number of drugs people are taking and increase the activity. So this is what I think is happening. We're injecting a drug, and because it stays around for longer, we are inhibiting the angiogenesis in the retina. So with that, I would like to thank my collaborators who contributed to this project. I'd also like to thank the TASSA conference. Thank you so much. This is a really great honor for me, so I really appreciate that, as well as my family.